this is lab number 4, friction. The in-person lab would have a similar setup as what you see here in this screen. All right, so let's talk about friction a little bit first, and we talked about the theory, and then we'll go and we'll explain the lab. So we have two different types of friction. First type is static friction. All right, static friction is always equal to the applied force. Let's say that I have a box here, mass m, and there's applied force F equals 12 newtons to this box. The static friction in the opposite direction, all right, F static, is equal to that applied force, which was 12 newtons. All right, if you keep adding more force to your applied force, for example, if you go from 12, if you go to 13 newtons, all right, then the amount of static friction would be exactly equal 13 newtons, all right? If you keep adding more force to your applied force, at some point, the box or the object is about to move, but it's not moving yet. That is what we call maximum static friction. All right, so F static max. At that point, the amount of static friction is not equal to the applied force, and it simply follows a formula. Mu s, which is a constant number, times normal force, n. All right, this mu s here depends on the surface. All right, it could be different combinations, and each material have their own mu s. So for example, wood on wood would have a different mu s, metal on wood would have a different, plastic, so on and so forth. So this mu s really depends on the material. All right, this n here is the normal force. And a lot of times we think that normal force is equal to mg, force of gravity, which is not always the case. So maximum amount of static friction is mu s, which is a constant, times n, which is the normal force. Okay? On the other hand, if you keep adding force to applied force, at some point the object, or a box in this case, will start to move. And once it starts to move, then you will have Fk, or kinetic friction, because the object is moving. So we use kinetic. In that case, we'll have mu k. It's a different constant. K indicates that it's kinetic. S indicates that it's static, times the normal force. And again, this mu k is different from mu s, all right? And it depends, these two both depends on the material, all right? So one thing that we need to know for sure, that's always mu k is less than mu s. All right? In other words, f of k is always less than f of s. All right? So the amount of kinetic friction is always less than the maximum amount of static friction, Fs max. All right? So this is a little bit of a background that we need to know before we start doing the lab. And so I'm going to very quickly explain what we would have done in an in-person lab. We'll have a combination. We'll have something similar to this. We have a wooden block here, right? We'll have an object which we call here M2 on that wooden block. This M2 has two surfaces. The first surface is wood, and the other surface is metal. All right. So the combination of the surfaces that we would have is wood on wood and metal on wood, okay? And then we'll have a string connected to another mass, hanging mass, M1. All right, we think that the friction is negligible. That's one of the assumptions that we always have. And we also think that there is no friction involved in the pulley, okay? We wanted to measure, the whole goal of the lab is to measure mu k and mu s. These are the constants that I talked about earlier for wood-on-wood combination. So wood-on-wood combination and metal-on-wood combination. That's the whole goal of the lab. And using this lab, we can figure out, or we can come to the conclusion that mu k is less than mu s. Okay, so let's take a look at the setup that we'll have, and we'll go from there. So let me first go ahead and show all the forces. We'll have force of gravity, okay, mg. This is m2 to indicate that we're talking about this mass, so m2g. We'll have a normal force, normal to the surface, remember. Surface is not tilted, so normal force is normal with an angle of 90 degrees with respect to the surface. We'll have a force of string, tension, all right? And we'll have friction here. I'm not labeling it F of S or F of K right now because I wanted to explain what we're gonna do. So if I keep adding mass to this hanging mass right there, M1 for example here, what's gonna happen is that friction will build up. We keep adding mass here, let's say with an increments of 10 grams. So M1, let's say you start with 100 grams. All right, and you don't see any motion, and the object is not about, M2 is not about to move. There's nothing, this 100 grams is not enough to keep the object moving. So you add another 10 grams. Nothing is happening. All right, another 10. Nothing is happening is still. I keep adding masses until, let's say you reach to, let's say 400 grams. At that point, the system is about to move, because if you just add one more gram to it, let's say you go to 401, then you see the object is moving. This box starts to move to the right, all right? So you would stop at that 400. So you keep adding masses in the lab until you see a motion, and then you go backwards. Basically, you say, oh, 100 grams, nothing, 110, 120, 140, all the way to, let's say, 400. And as soon as you add a little bit more than 400, you see the box is moving to the right. Then that 400 is your starting point. Okay? So this 400 hanging mass here, with that 400 hanging mass hanging, you see that the object M2, the box or the block, is about to move. It's not moving yet. I put emphasis on it. It's not moving yet, okay? So that 400 is the amount of hanging mass you need here so that your object is about to move. As if you add a little bit more mass to the hanging mass, then the system will move, okay? So if that's the case, then you would say that this force of gravity here, let me erase this, a force of gravity here, which is M1G, that's the tension T, this force of gravity here is equal to maximum static friction, all right? So M1G, which is this force, hanging force, force of gravity on the hanging mass, equals maximum static friction, which we already know what it is. It's mu s times n. Therefore, equals mu s n for the box for M2 equals mg, M2g. Okay, so let me also erase all of these. All right, so M1g equals mu s times M2g. I can cancel g from each side. This g can be canceled with that g. And if I solve this equation for mu s, what I will get is mu s equals m1 divided by m2. So that's the mass of the block here in the denominator. The numerator, what I have is the hanging mass, right? As an example, when I said it was like 400 something grams. And this is also given to us. So in the lab, what we would do, we keep adding mass to the hanging mass. We start from 100, we go to 120, 140, 200, 300, all the way. And at some point, the system will start to move. That's the point that I need, okay? So this m would be that mass, which will be given to you. And the mass of a block is also given. So that's how I can find mu s, or coefficient for static friction, okay? Now, the next part of the lab, part 2, is a little bit different. So let me go to part 3 first, and I'll come back to part 2. So we just finished part 1. Let's go to part 3. Part 3, what we're going to do, we are going to measure mu k. In this case, we need to know, or in fact, we wanted to know mu k, which is the coefficient for kinetic friction. So let's say that mass for hanging, the hanging mass required was 400 grams. This is just an example. It's not a real number, by the way. Take a look at the data that will be given to you. So M1 is, let's say, was 400 grams, okay? You wanted to go a little bit lower for mu k. The idea is this. For mu k, I'm going to go a little bit lower. So let's say 380 grams for mu k. And what then I'm going to do, I am going to tap with my finger. Using my finger, I'm going to tap to this right in front of the wooden block, or this block, M2. I'm going to tap here with my finger. I'm hanging a little bit of a less mass. In order to start the motion, we needed 400. But right now, I'm only using 380, so I'm using a little bit less. But this time, I'm tapping this area right in front. Basically, I'm tapping this path in front of the wooden block, okay? And what it does is that it will break the bound between M2 and the wooden track. So it will basically break the bound of molecules between these two different surfaces that I'm highlighting right here, okay? And so you're starting with a little bit less. The system was about to move at 400 grams, but right now I'm using 380, but I'm tapping this area, all right? I'm breaking the bound between the two surfaces. Now, the idea is this. If you do that, you will see this object, see this M2 move to the right, but the trick is that it needs to move to the right with a constant velocity. And we can measure the constant velocity using a laptop that kind of it takes into account the tangential velocity of this pulley, or you can kind of eyeball it and look at the motion of the box and say, hey, it's moving from this point to this point, and it looks kind of constant velocity to me, so you're good to go. So once you have that 380 or 390 or 395 grams for a mass of hanging, then you use the same formula. But this time, this same formula will give you coefficient for kinetic friction. Okay, so that was part 3. Now let's go to part 2. Part 2. In part 2, we are going to tilt the wooden block, the wooden track, with a mass M2, the block on it. And this time, what we're looking for is to get critical angle. Critical angle is, let's say that we call this critical angle theta C, C for critical. And basically, that's the minimum angle you need so that M2, the block, will start to slide down. All right. So let me show all the forces. The first force that we have is this force of gravity, M2G. Remember, gravity is always towards the center of Earth. Normal force, which is this force, normal. And again, surface is tilted, so my normal force is tilted. But remember, this will always make an angle of 90 degrees. Okay? And friction. F of S static. Okay, because the object's not moving yet. And the trick is here, what I need to do is to break this M2G into its components along X direction and Y direction. So here's my Y direction, and here's my X direction. And what I have to do is to have a component of M2G along the X direction. It's always M2G sine theta. This time I have theta C for critical. And M2G cosine theta. All right. So if you do that, if you basically break M2G into its components along the X direction and along the Y direction, you don't need to show M2G anymore. So what I'm going to do, I'm going to kind of erase it because I broke it into its components along X and along Y. All right. And remember, N along the Y direction, the object doesn't move. So N is always M2G cosine theta. And if you keep adding or increasing the theta, at some point the object starts to slide down. That minimum required angle, and that minimum required angle is called theta C or theta critical. At that point, M2G sine theta C is equal to your Fs max. Okay? Or static friction, maximum static friction. So here, I have M2G sine theta C equals Fs max is mu s times n, but I know what n is. I already found it here. All right, n is M2G cosine theta C. Okay, and so if you do that, then we can kind of cancel stuff. It's very easy. I can cancel G with G here. I can cancel M2 with M2. So what I'm left with is something very simple. Sine theta C equals mu s, mu s cosine theta C. Therefore, I can write it like so. Sine theta C divided by cosine theta C equals mu s. Okay, and sine divided by cosine is tan. So I have tan theta C equals mu s. All right, and then therefore, I can figure out how much is that angle. Theta C is tan inverse. You can use your calculator to find that, mu s. All right, so in other words, if you know mu s, you can figure out how much is your critical angle. Do we know mu s? Yes, we do. We found it in part 1. So in part 1, what we found was mu s, all right? M1 hanging mass divided by M2 mass of a block, which is giving us mu s. So we know what mu s is. We know this value. And so we can find how much theta c is critical angle is, the minimum required angle for the object or the box to slide down. All right? And then you would actually do this calculation with the information you are given. You would actually do this and figure out how much theta c is using this formula. All right? And then you want to do this in the lab as well. You have to increase the angle until you see that it's sliding down, and you would have stopped there. All right? So you can measure the critical angle in the lab by lifting one side of the wooden track up until you see that the block moves down or slides down. All right? So if you do that, basically what you would have is a triangle, right, similar to this. So you keep lifting one side up like so until you see that the block, which was here, M2, slides down. Then you would stop. And you wanted to measure this angle. In order to do that, it's very easy. You can measure this distance, right? Let's call it L. And you can measure this with a ruler or a meter stick. You can call it H. And sine of theta c, critical angle, is H divided by L. All right? Therefore, theta c is sine inverse H over L. All right, so this is in the lab. So you can actually measure theta c, and this is using a formula. This one is using a formula. So you can also calculate. And then the lab manual is asking you to compare these two values to see if they're close, if they're not, and what could be the reason if they're not, and things like that. All right, so this is what we do in this lab. Here's a little bit of a background. We'll show you a little short video of a lab setup, and then we'll provide you with all the information you need to complete the lab report. All right, thanks. So here's what our setup would look like. We have a block. One side of it is wood, the other side is metal, and we have a wooden track. We connect the block with a string to a hanging mass. The string goes around the pulley. And with a hanging mass, there's a mass holder, so we can add masses to the desired amount. So right now, the combination of the surface is wood on wood. We keep adding mass. We don't want to see any motion because at first we want to measure static friction, right, for wood on wood. And later on, we have to redo the experiment, but this time we would like to do the experiment for metal on wood. So we're going to flip the block because we would like to do it on a metal on the wood. So in the lab, you would actually do it twice, one for the wood on wood and one for metal on wood. You keep adding mass. You don't want to see any motion of the block because you want to measure the static friction. The amount of static friction equals to the force of gravity on a hanging mass, which is m1g. It's important to know that the force of static friction does not depend on the surface area. So we can actually redo the experiment again, one for the bigger surface that we did and one for the smaller surface. So we're gonna have the block on its side. Unfortunately, we don't have the smaller side for the wood on wood, but we can actually do the experiment for metal on wood. And that's part of the procedure for an in-person lab experiment. We redo the experiment, but this time we're going to use the smaller area. The next part of the experiment is that we're actually going to measure the critical angle as I explained. We're going to lift one side of the wooden track until we see a motion. This time you do not want to have any hanging mass. Then you have a triangle, right triangle. You're going to measure the height and you're going to measure the length, all right? So you can figure out how much is that angle, the critical angle. You want to stop where you see any motion of the block. So as soon as you see the block is moving down, that's where you need to stop and measure the height. Then you can measure the length and you can figure out what angle that right triangle has. Right, so that is the next part of the experiment, as we're trying to measure that critical angle. And there's a way to actually you can measure the critical angle based on mu s, and you have to compare those two values. The last part of the experiment, we're going to repeat what we actually did in first part, but we're going to have a little bit of a less hanging mass. Let's say that you start with 400 in part 1. You want a little bit less. Let's say you want 395. But this time the pulley is connected to a computer, and we would like to see a constant velocity of the block. So you add a little bit of less mass, but this time we're going to tap the wooden track. So therefore you see a constant velocity, as you're seeing right here. The block is moving with less mass, but you would like to see a constant velocity. You don't want it to see accelerating. You have to do it again twice, one for a wood on wood and one for a metal on wood, to measure mu k, which is a coefficient for kinetic friction. So two different surfaces, wood on wood, metal on wood. We do the same experiment to measure the coefficient for kinetic friction in our last part.